Welcome to another lesson on polar graphs, one of the most amazing topics in the world. You see a picture of 4 polar graphs in front of you. We have the rose curve, which could be 2 petals or 3 petals or 4 petals or even 1 petal. It looks a little bit different. A limaçon, say it with me, limaçon, which kind of looks like a lima bean. I think that comes from a French word meaning snail. But this is the one that looks a little bit more like a snail, the spiral of Archimedes. This is not the complete graph. I'll show you what I mean in just a moment. And then on the right bottom here is the Alumnus Kit, which is the infinity sign. This one we have to use 2 equations to sketch. So let me see if I could get the rest of the spiral of Archimedes. What you see here is starting at time equals 0 or theta equals 0. It actually goes the other way as well. So you get some sort of symmetry going on. It's not the best, but maybe you get the idea. Let's try it again here. See if I can get it. Yeah, I think that's the one. You kind of see a line of symmetry through the middle there. So these are the 4 we're going to focus on here, and it's really important that you have your calculator, your TI-84 graphing calculator in front of you. But if you don't, you could refer back to these pictures, and I'll try to help a little bit. But we'll be seeing a little bit different graphs from what we actually sketch. All right, so let's start with the rose curve, and basically what I have on top here is just the settings for theta, for x, and for y. It's kind of weird, even though we're in polar mode, we still have settings for x and y because it just gives you the screen settings. So now, like I mentioned in the last video, the theta step that you should have is pi over 24. So I'll jot that down. Theta step is pi over 24. And remember that I said once you punch that in, it turns it into 0.13. So if you ever see 0.13, you're probably in the right setting. So go ahead and enter these functions or these polar curves in your grapher. This would be y1 on the left and y2 on the right. And really, we just want to leave the first one on. So hover over the equal sign for the second one and press enter to turn it off. Pause me and then come back to that. All right, so now that 4 sine 3 theta is in your y equals, so it would be r1. Let's just take a peek at what that would look like. Now, if you don't have these window settings set, then you'll end up getting a graph that doesn't quite work. And the x's and the y's are in the ratio of 3 to 2. Okay, so when we take a look at that graph, what I want you to see, I'll go along with you here, is you basically have a 3-petal propeller or flower that's on the graph. And each petal only goes as far as the other petals. And how far that distance is being communicated by this 4 value. All right, so I'm just going to jot down a few basic things. First of all, I see 3 petals here, which connects to that 3 as the coefficient of theta. And then I also see that the max radius is 4. So pretend that you're standing at the origin, so 0, 0, and you're walking out to the farthest point of the petal. You're not following the curve, you're just walking straight out. The number of units that you would walk is 4. You could also sketch a circle around the propeller, and that would be a circle of radius 4, and it would just touch the tips of the petal. Okay, and then the final thing I wanted to say is that there is symmetry around the y-axis. So symmetry about the y-axis. And we could verify that algebraically if we wanted to, but that's not part of what I want to teach you today. We're just using a little bit of our analytical skills to see the patterns in some of the graphs. So other than how amazing this looks, real quickly, the domain of this function would be negative infinity to infinity, and we could seriously just plug in any theta we want, and it will just keep sketching. And if we go all the way up to, like, say 100 pi, it'll just keep sketching the same curve over and over again, so it keeps looping. And then the range of this curve is kind of unique. It's actually -4 to 4, and that's an r value. So that's the output, theta is the input, r is the output, and this is r as in range. Okay, so if you could take a look at your graph right now, what you'll see is that if you point in the direction of that tip of that pedal, you could also go backwards. So you could be pointing in another direction and walk backwards. So that's why the range is actually -4, goes all the way back to -4. So let's take a look at the other graph now. So I'm turning off the first one and pressing, hovering over the equal sign for the second one. And this one has cosine. And so if we would have sketched 3 cosine 3 theta, we would have noticed that there's symmetry only about the x-axis. But because this is an even value as a coefficient of theta, we end up getting 4 petals, and so there's tons of symmetry going on here. So I'll just jot that down, 4 petals. And if you're taking notes, this is stuff that you would just jot down. And then the max R value is not 4 like the last one. Max R value is 3. So that's a little bit easier to see on this one. If you're standing at the origin, to go all the way out to the tips of all 4 petals, you would walk 3 units. And then, like I said, the symmetry for this one is everything. So all 3, x-axis, origin, and y-axis. And I don't know, it's just very pleasing to the eye, I think. And then pretty much that domain and range that we used for the last one is going to be consistent for all of the functions that we look at today. So basically, if the max R value is 3, then the min R value is also -3. All right, so that's cool. It's something that you could show your parents, show your friend, be like, check out this cool rose curve. And I think there's even a shader function on your calculator. You could shade it in, but you could also press second zoom and turn off the axes, and it'll just show you the actual curve. All right, so that's rose curves, and you could play around. You could pause this video and punch in like 5 and 6 and 7 for the coefficient of theta, and you could see how you get tons and tons of rose petals with your graph. All right, so let's go back to y equals, and we have 2 more equations here. I have 2 more after this, and that'll be it for today. But so let's check out some limacons here. So turn off your other equations, punch these in, and come back to me. All right, so we have 2 plus 2 cosine theta. Now what's unique about this, I'll even just tell you before we graph it, is that I'm expecting there's going to be symmetry over the x-axis because we're dealing with cosine. So when I take a look at that, I see that that's exactly the case. Now my curve ended up looking red, but maybe yours is a different color if you have a color calculator. And so the first thing I'll just point out here is this is called a cardioid. Cardioid. It's basically kind of like a heart. And if you turn it sideways, it looks like the beginning shapes of our contemporary heart symbol that we use. And it is a cardioid specifically because the coefficient 2 cosine, the 2 in front of the cosine, is the same value as the 2 that's being added to it. So whenever those are in the ratio of 1 to 1, it's a cardioid, which is kind of cool. So this one has x-axis symmetry like I was expecting. If you flip it over the x-axis, it'll be symmetric. And then the max R value is a little bit easier to see with this graph than the very first one we saw. If you're standing at the origin, kind of that part of the heart where it goes in, you'd walk 4 units to get to the other side. But if you're facing in the direction of pi, or 180 degrees, you could walk backwards and go 4. So again, we have a range of -4 to 4. I'm actually a little bit shaky about that range right now. I'm wondering if it's just 0 to 4. And so anyways, just keep your eyes posted for some things that show up like that. The one thing we know for sure is that the max R value is 4. So I'll just jot that down. Max R is 4. All right, so that's a cardioid. There are 4 different types of limacons. We're just going to look at 2 here. So let's go back to your y equals and enter the other equation, or check out the other equation. Turn that one on. Turn the other one off. Okay, sweet. So this is basically a limacon with an inner loop. And that happens when that 3 coefficient is larger than the other number that's being added in front of it. So I'll just say inner loop. There's no outer loop cardioid or limacon, by the way. It's cardioid, inner loop, there's a dimpled limacon, and then a convex limacon. A convex limacon is just basically a circle with like a flat side. Okay, so it's not super interesting, but kind of kind of weird looking. So then notice that there's y-axis symmetry here because we were dealing with a sine function. So that's kind of nice. It's pretty, nice and pleasant on the eyes. And so basically what I want to point out also is that this negative sign, that 2 minus 3 sign, is what's making most of the curve go below the x-axis. So it's kind of a unique piece about that. And then one more thing, again, like the max R value, if you're standing at the origin or the pole, the max R would be 5. Ooh, that's kind of weird. You would maybe expect it to be like 1 or -1, but it's actually 5. It's really just the 2 added to the 3. So even though it's negative, it still has this max R value of 5. All right, so that's a limmason with an inner loop. Maybe I'll just share one more thing here. The form of a limmason is A plus or minus B, and then it's either sine or cosine theta. Okay, so one of those. It's kind of a weird formula right there, but that's the form of that. Okay, let's take a look at the spiral of Archimedes. So punch this R equals theta. That'll be quick, and then come back to me. And so I have R equals theta sketched. And this is weird. It didn't really pop up. Some of my settings are incorrect here. And so I have to go back and mess with them a little bit. And I only see actually half of the graph. So what I'm going to do here is, first of all, I want to zoom out. So go ahead and zoom out with me. Press zoom out, enter, and then enter again. So you could just see more spiral. And what you should see is just like one snail-looking thing, but go back to your window and make your theta max like, I don't know, 50 or something like that. Pretty big number. So then you'll just see more of the spiral, and you start getting dazed and confused or something like that. All right, now, it may seem like there's no symmetry, but there actually is for this particular polar curve. So go back to your window, and for theta min, put -50. And then you'll see the curve go both directions. It really starts from the outside. So this has y-axis symmetry, even though we didn't really expect that. And at first we had to just change some settings. And then the domain and the range would be -∞, infinity. Pretty amazing. So that's kind of a cool looking thing, especially watching it graph and turning off the coordinate axis for that particular one. So show that to your friends. So wrapping it up here, the last one is Alumnus Kit, and not a biscuit, Alumnus Kit. So the weird thing about this is that you have to actually enter this in 2 parts. So you might have run out of space. You might only have 6 particular R functions that you could enter into your calculator. So you could just erase one of those. But I want to share just a little trick with your calculator to plug this in. So first of all, we have R equals 3 sine 2 theta square root. Okay, so we're solving for R. But then we also have R equals -√3 sine 2 theta. So I guess our calculator, it's pretty difficult to actually sketch this in just one function. So what I'd like you to do is put this first positive one into R5, and then, so pause me for that, and then come back and I'll show you the shortcut for that. Okay, so you have that in there for R5 or R1, whatever, it doesn't matter. You have it into an R function. And then the next thing I want you to do is go into another R function and press the negative sign, which is, in the bottom next to enter. And then instead of typing the whole thing again, which is not a big deal, press alpha trace and then choose the function that you have the positive one in. For me, it's R5. And then go ahead and graph that bad boy. It should look pretty amazing. So you should have something that looks in R6 is that equation there. Now, if you already zoomed out, go ahead and zoom back in, and maybe your settings are still graphing like mine. Oh, that was silly. So to stop it from graphing, press second mode, or if that doesn't work, press second on. And then you could just go back into your window and change the theta min to 0, theta max to 2 pi. And then you'll be back to some normal settings. You could hit graph, And then still, you might be zoomed out, so then just zoom in a few times. Zoom in, enter, enter, zoom in again, and enter. Oh wow, that's so interesting. Okay, what happened for me, I wonder if it happened to you, is that it actually, the graphing calculator sketched both of these curves, one in green and one in yellow, or basically it sketched it twice. So it seems like we only really need one of these. I don't know if that's always the case though, so I would be sure to sketch both of them. The other thing that's weird is that whenever the curve doesn't seem like it completes, maybe you have to go more pi. So I'm going to make my theta max 3 pi. Okay, so the issue is sometimes the graphing calculator, because the line is so vertical, it won't actually sketch it. So I'm just playing around with the settings and making my theta steps smaller, like 0.05, 0.005. 0.05, that's it, okay. And then it sketches a little bit more of the curve, and I'm kind of zoomed in a little bit too much. Okay, well hey, that is all I wanted to share with you. Hopefully you can see some of the beauty of the curves that we've sketched, and you could try sketching other curves like r equals tangent theta, or r equals tangent over sine, or whatever. You could play around with all the settings and see what other curves that you can come up with. Alright, thanks for learning with me. Bye-bye.